In the last video, we saw two acceptance criteria for a PDA, and depending on that acceptance criteria, the language is defined, the language accepted by the PDA. So we cannot just say the language accepted by the PDA, we have to say the language accepted by final state by the PDA, or the language accepted by the empty stack by the PDA. And final state was, I'm starting from this initial configuration with this input W. If you can reach ID where the state is something which belongs to this set of final states, so then you accept this string. So all the strings that you accept through this criteria, so that together constitutes this language L of M. And a language accepted by empty stack was all the strings such that if you give that string as input to your PDA, starting from this initial configuration, it can reach a configuration where it has consumed all the input and the stack has become empty. So in here also, it has consumed all the input, but here the only thing is that this state has to be a final state and the stack can be anything. Here the state can be anything, but the stack has to be empty. And while defining this, while using this criteria, we generally keep this f as empty because that is not required. And in general, for the same machine M, you can get two different languages. One is L of M, one is N of M, and they in general may not be same. Okay. So this is what we said last time. But still there is a kind of equivalence. So this is the equivalence we will prove. So though for a given PDA M, this L of M and N of M may not be equal, but if you have some language which is say L of M for some M, the same language can be accepted by empty stack by some other PDA M prime. Okay, so we are changing the PDA, but the point is this language is important, right? So if you have a language L which you know, so suppose this language is L and you know that this L is actually L of M for some M, right? So then we show that this L is also N of M prime for some M prime. So N of M prime is language accepted by empty stack, L of M is language accepted by final state. So as we defined here and here, right? And similarly, the converse is if you have some language L which is say N of M for some M, right? So that means it is some language which is accepted by some PDA by empty stack. So then we show that there exists another PDA M prime such that this M prime also accepts this L via by final state criteria. Okay. So the equivalence comes in this form. So these two statements are equal, that is, there exists a PDA which accepts L by final state and there exists a PDA which accepts L by empty stack. So these two statements are equivalent because you know that if there exists some PDA which accepts L by final state, then there also exists some other PDA which accepts L by empty stack and vice versa. So these two statements are equivalent. So this is what we are going to prove now. Okay, so let's first prove this one. So suppose you have a language L which is accepted by some PDA M. So this PDA M is given and this L of M is defined. So we will construct another PDA M prime such that this language is accepted by M prime via empty stack. So this N of M prime is language accepted by M prime via empty stack. So yeah, initially this M is given, so we will construct this M prime so that this happens. So M is defined like this, what we discussed earlier as a formal definition of PDA. Now we construct this M prime by slightly modifying this thing, and the modification are as follows. So here we take all the states of M, but then we also introduce two new states. Okay, so one Q0 prime, another QE. Okay, the sigma is same because we are talking about the same language, so it's over the same alphabet. We take all the stack symbols of M, but we also add one more stack symbol, one new stack symbol for this M prime, and this new stack symbol for M prime will be the start symbol for M prime. Here the start symbol is Z0, so here the start symbol will be X0, and this X0 is the new thing that is here. Otherwise all the other symbols are taken from here. And this is phi because we are trying to accept, I'm talk about the language n of M prime, so it doesn't matter what this f is. So as we said earlier, it is kind of customary to keep this as phi, this final state as phi. And obviously the whole the main thing is to define the transition function. So here we have a new transition function delta prime, and delta prime is defined as follows. Again, you see that if you concentrate on this this rule 2 for constructing this delta prime, so you will see that it is almost equal to this delta. Okay, so why? Because you see that so delta contains this sort of pair, right? So the first component is a state and the second component is a string over stack alphabet. So for all q, the small q in q, for all symbol or this epsilon, so whatever can go in here, and for all stack symbol z, not x0. So this x0 we will define later. So so for all this thing for which this delta is defined, if we have a pair here, so then we also have that pair here. So in that sense they are kind of equal. So this 2 says that this delta and delta prime are essentially almost equal. But we said that the start symbol is x0 here, right? So what will be the initial ID for this M prime? So and also the start state is q0 prime. Here the start state is q0 and here it's q0 prime. So this will be the initial ID for M prime. So this is the start state. This is the start symbol. So it's not ID. I mean, so the initial ID will be something like this. So you will have start state here, start symbol here, and the input here. But from this combination, if you see this state and if you see this stack symbol, for this combination we define a epsilon transition for this M prime. Okay, so this delta prime is for M prime, so we define a epsilon transition which just changes this to q0. So see, q0 is the start state for M, right? And it pushes this z0, right? So it replaces x0 by z0 x0. That means it just pushes this z0 over this x0, right? So if you have some steps in M starting from here, so this is the initial ID for M. So the corresponding thing in M prime will be if you provide the same input, it starts from here, and then using this epsilon transition, it doesn't process any input symbol here, but it changes the state to q0 and it changes this x0 to z0. So you see that from here to here, you compare these two things, it has just pushed this x0 in the bottommost position. Okay, so otherwise this part is same as this one. And by virtue of this rule 2, because all other transitions are same, essentially same, so if you have number of steps here for m which leads to this id, so then you will have a corresponding number of steps here. So what is the difference? This is same, the intermediate IDs will be same except for the fact that the leftmost position is x0. Okay, so this extra symbol is here. So you take all the intermediate IDs here, the corresponding IDs here are same except that the rightmost symbol is this x0 throughout. So if you can reach here, you can reach here. Okay. And this is, if this W is accepted, that means you reach some ID where this Q is a final state in M, right? Because M is accepting W via final state. So this Q will be a final state here. Now here comes rule 3. So this is how we construct delta prime. So if Q belongs to this set of final states, then for any stack symbol in M prime, because you see it also contains this x0. Okay, so for any stack symbol for this thing, it makes a epsilon transition. Okay, and what does this transition do? So you see that so this means that it's a epsilon transition. That means it doesn't read any input symbol, but it changes the state to this QE from this Q, which is a final state here in M. So it changes the state to QE, and it replaces Z by epsilon. That means it just pops this Z. Okay, whatever symbol is the current top stack symbol, so that it just removes this thing, it replaces by nothing. So corresponding to this we were here, so this part corresponds to this part. So now from here, using rule 3, what will happen, because this is a final state, this is a final state here, so from here it will make a epsilon transition. It can make a epsilon transition. So this is happening in M prime. See, this is M and this is happening M prime. So the state changes to QE, and no more input symbol is processed. So here already we have processed all the input symbol. So the remaining input is epsilon, right? So here also the head doesn't move any further, so it's okay. It's not undefined or anything. So the read head doesn't move, all the input symbols are consumed, but so sorry, this this should remove the top stack symbol. So here is a typo, so I should have a ZM minus 1 here. So this should be ZM minus 1. Okay, because the ZM will be removed, right? And then in M many steps, sorry, here we have M plus 1. So then in M many steps, what will happen? So here we use this rule 4. Now once you are in state QE in M prime, so this Q was particularly introduced in M prime, you remember. So the whole purpose of introducing this QE is to empty the stack, because you see what's happening here. If you are in QE, okay, you are making epsilon transition, so you are not doing anything to the input symbols. So you have already exhausted the input symbols here, and the transition says that you do not process any more input symbols, so that's fine. But it just removes the current stack symbol, because this is current stack symbol and this is being replaced by this epsilon, right? So the whole purpose of introducing this state QE is that once you enter this state QE, you stay in state QE, but then you just keep on removing the top stack symbols. So it then removes ZA minus 1, then ZA minus 2 up to Z1, and also this X0, because this happens for all stack symbol for this M prime. So you see that it will reach this thing. Okay. So this shows that if you can accept a string in M via final state, so the same string is accepted in M prime via empty stack. Okay. So we need to prove the converse also, but the converse is also easy to see, because now if you say start from here, so we just prove if this is true then this is true, but this is if and only if, because suppose you are accepting something in M prime via empty stack, so that means you started with this ID and you have some after some number of steps you have some empty stack. Now you see that the first step is to push this X0, right? So, and once you push this X0, once you have this, so then you have this Z0 here, and then you have this Q0 here. The remaining steps will be the steps which you will have in M, right? Because all the states you will encounter, all the stack symbols you will encounter, so they correspond to this thing, and by this rule, so this delta prime is same as delta for those things. So for some number of steps you will just carry out simulate this M, right? So now how can you go to a empty stack? So to go to empty stack you have to remove this X0, right? And how can you remove X0? You cannot remove X0 by any transition in here in this rule 2, because it is just copying the transitions of M, which does not have X0. You see that this is for this Z belonging to capital gamma. So all these transitions, so they cannot remove this X0. So for that you need to apply this, you need to encounter this thing, okay, this sort of transition, this transition. If you are moving from, so you start with this, so that means you are bound to be here in the next step, and from here if you are reaching the empty stack, so at some point of time you must remove this X0, right? So that means you have to, and when you are removing this X0 you must enter this state QE. So that means you have to enter the state QE, right? So this is the argument, and once you enter state QE you remain in state QE. Okay, so you understood the argument. To reach from here to here you have to remove the symbol X0, and you can only remove symbol X0 using this thing, and that ensures that you enter state QE. And because the state QE has this property that once you enter this you remain in state QE, that means so this will be QE, and at some point of time you entered QE and remained in QE. and that part should be this, because when you are in QE and you are continuing with this state QE, that can only happen via this transition, which just removes the stack symbols one by one. Okay, so you have to have a trailing part like this. So if you are accepting any W via empty stack in M prime, the path for acceptance has to look like this, and then this part from here to here will exactly correspond to a path like this in M, which will mean that this W is accepted via final state in M, because in order to enter this state QE, so you can only enter state QE if you have already come to a state which belongs to F. So that means at some point of time you reached this final state from here to here. So that means yeah, okay. So this is the proof idea. To properly do this, you have to use inductive argument as always, but yeah, if you want to write down the entire proof, you can do that. That will be a good exercise for you. But this is the proof idea. Okay. So now we prove the other part. That if you have PDA M such and you consider the language which you accept by M by empty stack. Okay, so n of M. So then there exists a PDA M prime which accepts the same language, this n of M, but this is L of M prime. So M prime is accepting this language via final state. Okay. So that means given M, again we will construct this M prime and so show that the languages are equal. So here again we introduce two new states. Okay. And since this is a PDA which accepts and the language we are considering is n of M, so okay, so this should be phi. So this F should be phi. Okay, and here this F is just one, it consists of just this one state QF. So this will be our only final state in M prime. So we introduce this QF, and like before we introduce a new start state which is Q0 prime. So these are the two states we introduce in M prime, and like before we also introduce this new start symbol x0. So we have this with the other symbols, stack symbols of M. Sigma will be obviously same, and then this delta prime will be defined like this. So this is what we have done before. So it just so it is relevant at the start. So this is now I'm going to show that if some string is some string is accepted by M via empty stack, if and only if that string is accepted in this M prime via final state. So this will be the initial ID in M with input W. So here the start state is Q0, start stack symbol is Z0. So here it will be Q0 prime and X0 prime, and as before the first step will be this. So this epsilon transition, this only thing that we have here. So it will change the state to Q0. It will do nothing to the input, the remaining input. I mean everything is remaining still, but it will just push this Z0 on top of X0, right, like before. And then so this rule 2 is again like before. So for all other stack symbols, so excluding this X0, if you just consider this gamma, and for all other symbols in here sigma or epsilon, all states for this Q. So for this they are equal. Okay, this delta and delta prime are equal whatever is defined here is exactly defined same as it's exactly same here, whatever is defined here. So yeah, if you are making some number of steps here, so you can make the same number of steps here, but like before, the rightmost stack symbol here is x0. Otherwise, the remaining part of the stack kind of changes exactly same as this thing. Whatever you have here as your stack strings, so the same stack strings you will have, but that with the rightmost symbol as x0, right? And then here you are accepting this via empty stack, so you would reach this as epsilon. So that means here everything is exhausted. So starting from this z0, whatever you have in between, so after that you have removed everything. But here we had this extra x0 throughout. So that means here when you empty everything, the corresponding thing here is that you just have this x0 because everything else is removed. So it's like epsilon x0. So this z0 corresponds to z0 x0, and this epsilon will correspond to epsilon x0 here. So yeah, this many transitions guarantees that we have these transitions here. And once we have this transition here, then this rule 3 will kick in. So it says that once you see this x0, so that means so it's like you are simulating this m with m prime, and when in m prime you see x0, that means in m actually it was empty stack. So in that case you switch to this state qf, okay, and you remove this x0. So it is not relevant. So this part can be anything because we are just switching to qf, which is the only final state here, and it accepts this thing by qf because it has already exhausted this w. So this has already become empty and it has reached a final state, so it accepts. And here also so we proved this direction, but the opposite direction is also true. Why? Because if you are accepting anything here, that means by final state, so that means you have to enter this state qf, where this is epsilon, so all the input strings are consumed, and you can enter this qf only via this transition, okay. So you can enter this qf only if you have x0 as your stack string. So there is not stack string, if you can see this x0 as the top stack symbol, but when can you see this x0 as your top stack symbol? See, the first thing is that you push this at the very bottommost position. So then while processing, this x0 is uncovered in m prime. So only if you can have this ID in m, okay. So this direction is also kind of clear. So you can only enter this f if you have empty stack here. So again, these I have written this as a proof idea, and it's quite clear from this, but to formally write down everything, to pin down all the thing, you have to again use induction on this I, okay. But we have done this 1,000 times by now, so you should be able to do it yourself. This is the proof idea. So that means we now have proved this thing, that if L is accepted by a PDA via empty stack, by empty stack, that is equivalent to saying that L is accepted by a PDA by final state. So the next thing we will prove is that if L is accepted by a PDA, so now the PDA accepts language L, so I mean it's no longer necessary to say that whether it is accepted by empty stack or final state, because in this statement what are we saying? If L is accepted by a PDA, then the L is CFL. So if the L is accepted by a PDA via final state, then it also is accepted. In fact, if and only if it is accepted by a PDA by empty stack. So this part we need not specify whether this PDA is accepting via empty stack or final state. So it says that if L is accepted by a PDA, so then L is a CFL, and similarly if L is a CFL, so then it is accepted by a PDA. So there exists a PDA which accepts L. In fact, while proving these two theorems, actually we will use the criteria of empty stack. So we will prove something like this, that for any CFL L there exists a PDA which accepts L by empty stack, and if a PDA accepts a language L by empty stack, then L is a CFL. So this is the thing we will prove, but this is same as saying that the PDA accepts it by final state, because that is what we just proved, right? So next move to the next theorem. So